Okay, so I'm going to keep talking about limits, and we are going to prove a limit rule today. Um, so if you recall, we say that the limit as x approaches a of f of x is L if for all real numbers epsilon greater than 0, there exists a real number delta greater than 0, such that whenever we have an input x such that the absolute value between x and a is between 0 and delta, whenever we take such a value x and plug it into f of x, we're going to find that the absolute value of f of x minus L is smaller than epsilon. Okay, we saw that definition before. I was just reviewing. So today we're going to prove a rule for limits, which is basically, this is a well-known rule. This is something that you all learned in Calc 1, that if I have two functions f and g, and say the limit as x approaches a of f of x is L1, and then the limit as x approaches a of g of x is L2, then when I add the two functions, when I do f of x plus g of x, and I do the limit of that as x approaches a, I just get this limit plus this limit. In other words, I get L1 plus L2. So this is something that we all learned. Maybe you've seen a proof of it before, but probably most people forgot. And actually, probably most people never saw a proof of it. This is something in Calc 1 that is often stated without any proof. So we are going to prove it, but before I do that, let me do some scratch work, because if I just pull this proof out of nowhere, it's going to seem like it came out of nowhere. So scratch work. Whoops, we're blurry. There we go. Well, in this theorem, I get to assume that this limit is L, or that this limit is L1, and that this limit is L2. So let's talk about what I know. I know this limit and I know this limit. Now let me translate this. I know that for all, okay, let me use, I'm going to use the subscript 1 for this situation. So for all epsilon 1, there exists a delta 1 such that this implies this, right? Because I know the limit of f of x is L1. And also, I know basically, so the same thing for g of x and L2. So for all epsilon 2, there exists delta 2 such that this would say the same, whoops. Okay, yeah, sorry, I won't be lazy. 0 less than delta 2 implies g of x minus L2 an absolute value less than epsilon 2. Right? What do I need? I need to show that this is this. In other words, I need to show for all epsilon there exists a delta such that this implies, so what do? I take the function minus the supposed limit. So that would be f of x plus g of x minus this. Is less than epsilon. So I didn't do a whole lot just now. I just translated because the statement, whenever you make a statement like this function has this limit, that means an equivalent statement about some epsilons and deltas. That means for all epsilon there exists delta such that blah blah blah. And I just translated these two statements, which these are our assumptions, and then I also translated this statement, which this is our desired conclusion, and I just translated all of them in terms of epsilons and deltas. So that's all I did, which may not be too much, but a lot of math is just translating statements into other statements until you realize that you've arrived at something more or less obvious. So what am I going to do now? I am going to focus on this. How can I guarantee that this is true? So here's something to observe. If I do this, I can group these things together, f of x minus L1, g of x minus L2. Right, that's the same thing. I didn't change anything. I was just rearranging stuff. And here I have f of x minus its limit, because remember f of x was going to L1. And then I also have g of x minus its limit, because g of x was going to L2. And I like grouping things together like that. I like grouping f with its limit and g with its limit. What am I going to do now? I'm about to apply the triangle inequality. If you remember the triangle inequality, this is valid for all real numbers. If I have a plus b in absolute values, that's less than or equal to absolute value of a plus absolute value of b. And this is true for all real numbers, a and b. So that's what I'm about to do. This number will be my a, this number will be my b, so this is less than or equal to this one plus this one. So I like this because, right, this one, I know that I can make this smaller than epsilon 1, like this absolute value of f minus L1. I can make this smaller than epsilon 1 if absolute value of x minus a is between 0 and delta 1. And similarly, I can make this one smaller than epsilon 2 if x minus a and absolute values between 0 and delta 2. So then if that's the case, then this would be smaller than epsilon 1 plus epsilon 2. What do I need out of this? Again, for this, I was just going to be less than epsilon. So I could make this less than epsilon, or actually, why don't I make it less than or equal to epsilon? I already have a strict inequality here, so I don't have to worry about the fact that this is strict. Yeah, so sorry, I lost my train of thought, but all I'm saying is that I can choose epsilon 1 and epsilon 2 to just be epsilon divided by 2. That way, you know, this is epsilon over 2, this is epsilon over 2. They add up to epsilon, so I'm choosing epsilon 1 and epsilon 2 to make sure that this is true. And that's important because all of the the important part about that is just the fact that if epsilon's a positive number, then epsilon 1 and epsilon 2 are also positive, because they would be a positive number divided by 2. And all of these numbers, epsilon and delta, they're all supposed to be positive numbers. Okay, so how do we turn this scratch work into a formal proof? It looks like right, okay, so let me start over. All of these limit proofs start with the same line. It's let epsilon be greater than 0. And in the end, I have to show the existence of a delta such that this implies this about whatever the value of epsilon was. So I'm going to start a proof that way. I'm going to say let epsilon be greater than 0. And then I'm going to define these numbers epsilon 1 and epsilon 2. And those are going to be that number epsilon, half of it. And then I'm going to make these statements. So, yeah, why don't I quit talking and start writing? Let epsilon be greater than 0. And define my two numbers, epsilon 1 and epsilon 2, to just be half of that. Now I'm going to say what I need to say about epsilon 1 and epsilon 2, meaning so there exists a number delta 1 and also a number delta 2 that are positive, such that two things. It's these two things. So this implies this, and this implies this. Okay. So how is the rest of this proof gonna go? I need to start talking about this quantity, and I know what I'm going to do with this. I'm going to break it up using the triangle inequality. I would like to, okay, let me try to, since I've already done scratch work, let me try to think a couple of steps ahead here. In order to make these things what I need to make them, because once again, I plan to take this, I break it up using the triangle inequality. I've got this part and I've got this part. I want to make this part less than epsilon 1. I want to make this part less than epsilon 2. But in order to have that, in order to make this one less than epsilon 1, I need to have this. And in order to make this one less than epsilon 2, I need to have this. In other words, this absolute value of x minus a, it needs to be, first of all, it needs to be greater than 0. That's the same for both of these. Second of all, this number has to be less than delta 1, and it has to be less than delta 2. So here's what I'm going to say. For the purposes of my proof now, I really... I need a delta. I guess that's what I'm talking about. I have a delta 1 and a delta 2, but I need a delta, like, for the value of x to be. Let me feel like I'm not explaining this the best way, so let me just say exactly what I mean. I'm going to let delta be the min of delta 1 and delta 2, whichever one is smaller. And by the way, this is a positive number. If delta 1 and delta 2 are both positive, then the min of them is positive. And why do I do this? Why is it the min? It's because if I let this be the min, and now I say that absolute value of x minus a is between 0 and delta, this number is less than or equal to either of these because it's the smaller one. So this would imply, I mean, if this is smaller than delta, then it's smaller than delta 1, and it's also smaller than delta 2. Meaning that I have both of these, right? Because this number is smaller than epsilon 1 as long as this is smaller than delta 1, which it is. And this number is smaller than epsilon 2 as long as this number is smaller than delta 2, which it is. So that's the purpose of the min. Okay, so now that that's out of the way, then I think this won't be too much harder. So I start talking about this thing. I'm really ready to talk about it now. I break this up using the triangle inequality into this. So that's f of x minus L1 and g of x minus L2. I know that this number is less than epsilon 1 because x minus a, this absolute value of x minus a is positive because of this, and it's less than delta 1. So that's why I get this. And then similarly, I get this is less than epsilon 2. But oh, look, we chose epsilon 1 and epsilon 2 to both be half of epsilon, so then when I do this, this is just epsilon. So I got it. I got that this implies that this is less than epsilon. And yeah, so in the end, it's easy for this to feel extremely technical, and to lose track of what we're doing. But it is it is intuitive. At least parts of it are intuitive. Um, Once again, we're claiming that if this function approaches this limit and this function approaches this limit, then the sum of these two functions approaches the sum of the two limits, and a proof of that really should involve having to say, how close is this one to its limit, and how close is that one to its limit? Because if this number is close to this number and this number is close to that number, then when I add these two numbers, it should be close to the sum of these two. And all of these expressions that you see, like the absolute value of one number minus another number, like here we see the absolute value of x minus a, and here we see absolute value of a different number minus a different number. All of these things are talking about how close two numbers are. Like this is saying that the distance between x and a is less than delta 1. And this is saying that the distance between f of x and L1 is less than epsilon 1. And in the end, if you look at the last line of the proof, we basically showed that this difference, which is meaning like the distance between the sum of the functions and the sum of the limits, we took that and we expressed it in terms of how close f of x is to its limit and how close g of x is to its limit. And if this is very close and this is very close, like this distance is at most epsilon 1 and this distance is at most epsilon 2, then the sum of the two functions is close to the sum of the two limits. And there's some technical messing around with inequalities and stuff like that, but the proof isn't too bad. It can be seen as intuitive in a way. Okay, so let me upload this and try to make another one.